Hello again, everyone. So I will talk to you now briefly about multi-scale challenges and specifically about dark field imaging. So in the type of science that we're doing, the scientific questions often have an intention. So we want to answer research questions about the macroscopic behavior of materials. So for example, if we want to study salt efflorescence, then that's a macroscopic behavior. And we can see that as we walk down the street that we have these salt precipitations on the surface of mineral building materials. But we know by now that this actually happens due to the microscopic behavior of moisture and salts within the pores of the material. So studying this effect requires us to study the microscopic behavior of the material. So knowing that as a research question, then we know, okay, we need to study the microscopic behavior of our samples. But still, the next question then is, what do you mean with microscopic behavior? Do you mean the millimeter range or the micrometer range or the nanometer range? Well, unfortunately, in many mineral materials, the answer is, well, the entire range, because the pore space, if that's what you're interested in, it ranges that entire span. You have pores of millimeters or even centimeters in size sometimes, and in the same material you can have pores that are smaller than that are in the nanometer range. So that's a huge range to span. Luckily, we have many modalities that allow us to cover that range. So the situation is not as bad as I'm making it out to be, you might think at this point. There are a number of side points I need to make here. So on the one hand, we have these modalities, and that's great, you might think. But the modalities that I have on the slide here, like mercury infusion porosimetry, optical microscopy, and electron microscopy, if you want to study a volume, so a 3D, if you want to create a 3D data set, then you need to remember that these are destructive methods, because for example, for the optical microscopy, you can only image the surface. So if you want to make a 3D volume, you have to destroy your sample in doing so. And that's not so ideal if you want to do reproducible, want to study using multiple methodologies. Luckily, the technology that we have been studying today, X-ray CT, well, that is a non-destructive methodology. So that does allow you to study objects in 3D without destroying them. And the difference has been talked about today by Veerle and others before as well. You have synchrotron sources, you have lab-based sources, and they vary in capability. And in fact, if you ask the question, what is the length scale range of a synchrotron facility? Well, that can actually go down to the nanometer range if you try real hard. So you might think, okay, problem solved. We will just use a synchrotron for everything, if that were possible at all. But that's not possible because when you choose a length scale, that comes with its own particular challenges still. So you might decide that you want to study pores of the size of millimeters. Well, if one pore is the size of 1 millimeter and you need statistically sufficient number of pores to make a statistically relevant study, then your sample has to be centimeters in size. If your sample is centimeters in size, then it's impossible to move it within millimeters of the X-ray source. And that is what is needed if you want to achieve a very high magnification. So you need to move it a sufficient distance away from your source. And that limits the magnification that you can achieve. So that also, by limiting the magnification, if you remember that equation that I had in my earlier presentation, that limits the resolution that you can achieve. You can achieve with these modalities a higher resolution, but that requires a higher magnification, moving your sample closer to the source essentially, and thus that requires a smaller sample. So you have this inextricable link between the size of the sample and the magnification, and therefore the length scale that you can do your studies on. So it's a trade-off. It's a tug of war between having a smaller sample to work at a finer length scale and a larger sample to work at the coarser length scale, while you still need to keep in mind that you always need to study a representative elementary volume to get sufficient statistics for the study that you are attempting. And here's a very visual example. Thank you, Vele, for providing this slide to make that exact point. So this is the same sandstone material that we were so fond of. And on the left, you see the reconstruction of a 40 millimeter core sample of the sandstone using a medical CT device. And here you see a micro CT image of that same sample. And to the right here are two smaller samples that are imaged at a higher magnification and therefore a higher resolution. And you can clearly see that the micro CT achieves a higher resolution, and that's because of this magnification factor. And actually, this is a very nice example of the principle that I explained this morning in resolution, saying that a point spread function blurs out everything. And you can see here that because the medical CT has less magnification, it has a wider point spread function, and thus it is blurring out more, making the resolution lower, because now you can no longer make out the individual pores, the individual peaks in your signal, while you can do that to some extent in this example. So long story short, if you want to cover the entire length scale range, you often need to resort to using multiple image modalities or using one modality at different magnifications by studying samples of different sizes. One of the more novel modalities that we have been working on in our group is called dark field micro CT, and that's what I'm going to talk about next. It's a modality that promises to go even further down the range of non-destructive characterization of materials in the nanometer range. And I will try to give you an explanation as to how it works. So it is still micro CT. So you have all the conventional elements of a micro CT imaging system. You have your X-ray source, you have your detector, you have your sample on an automated stage, and that's a crucial novelty in this type of imaging. You have gratings. Now these gratings, you can think of them as being these very fine line structures, and there's two of them, and you place them in between your detector and your sample. That's one way to arrange it anyway. So you place them in your geometry, and then you acquire your projections, and you acquire multiple projections because while you're doing that, you're also doing phase stepping, and phase stepping means moving one grating with respect to another. Now these gratings, they are these line structures, and they change the phase of the X-rays passing through it. And if you're playing with the phase of X-rays, that means that you can use this to generate interference patterns. And this interference is actually what dark field imaging relies upon. I will explain that in a bit more detail here. So if you have a grating, and you measure the signal intensity on one detector pixel, then you will measure a certain flux, you measure a certain intensity. Now, if you move that grating, then you are shifting the phases and you are shifting the interference pattern, and because of that, you will measure a different intensity. So as you move the grating, you can, and each time you sample the intensity you measure in your pixel, you will actually measure an interference pattern in every detector pixel. That is the basis of dark field imaging, because that interference pattern, it has an amplitude. So this sine wave, it has an amplitude, and that amplitude is called the mean visibility. So that's the start of any dark field experiment. You measure this mean visibility. Then you insert your sample in your geometry, and you do the same thing again. And what you will have noticed is that the phase of this interference pattern changes, and the amplitude will change as well. And that change in amplitude, that's called divisibility reduction. And that visibility reduction is the signal in dark field imaging. Because if your sample is chaotic internally, that interference pattern will be gone because all coherence is lost, and the visibility will be set to 0. Well, if your sample is really homogeneous, then not a lot will happen and your visibility will remain. So this tells you something about the substructure. In fact, people have studied this, made a theoretical model about this, and they came up with a characteristic length for a dark field imaging system. That characteristic length is called the correlation length, and it depends on a number of things. One being the effective wavelength, so that's the energy of your X-ray photons. The other being the distance between your sample and the grating. And the other being the pitch of your gratings, so the distance between the high and the low point of your phase shifting grating. And this correlation length tells you something about the length at which you are studying your sample. And I will explain that, trying to using an analogy here. So here you see two voxels. So this is a voxel and this is a voxel. And because we have magical eyes now, we can really see what is happening inside a voxel. So here we see a hypothetical substructure of what is actually happening in the voxel. And here we see it as well. And as you can clearly see, the length scale is different between the two. Now, this correlation length, as I said, is defined by system parameters. And you can think of it as being a shift of the substructure with respect to itself. So we shift it by this amount, this correlation length, and then we see how well that structure within the voxel correlates with itself. And what you'll notice is that if you shift that to a larger extent than the characteristic length at that scale, you will see a lot of incoherence, really. You will see a lot of color. So everything here that's either purple or green means a mismatch between the shifted version and the signal itself, and here as well. And so you will see that the autocorrelation is different when you shift it more than the characteristic size of an object. And that determines how much of the visibility of your dark field signal is lost when you do this. I will show you an example to make this more tangible. So suppose that we are imaging a cylinder of material. We create an absorption image using conventional CT, then you may get something like this. Then you insert your gratings, you do your phase stepping, and you image the dark field signal or the visibility reduction, and you get something like this. And now you change the geometry of your system to change this autocorrelation length. How is this achieved? Well, the geometry is determined by this L, that's the distance between the sample and the second grating. So we move the second grating, and thus we are now imaging at a different correlation length, and we see indeed that the visibility reduction changes, this time lighting up the top area. That indicates that the top area loses a lot of visibility at the length that's corresponding with this correlation length, which then corresponds to a size in the nanometer range. So it's really giving you information about what's happening inside your voxels in the nanometer range, which is a really interesting observation. Now, to finish up this brief introduction in dark field imaging, I will show you some results of our own research in this respect. So what we did is we have taken a material that we have broken down into particles of a size of a few hundred micrometers, and we have arranged them into cylinders, where the two materials were made out of discs that had a different size of characteristic pores. So the one material had characteristic pores of size of 150 nanometers, and the other had characteristic pores of size 50 nanometers. And then we stacked them one on top of the other, and we also made a sample where we mixed these particles. And as you can see in the X-ray absorption images, there's no difference to be made between them, and the reason is obvious because the resolution here was in the range of 2 micron, while yeah, these pores are far smaller than that. Nonetheless, if you do the dark field acquisition and you then build a signal processing pipeline to remove the noise and to extract the parameters, you can actually try to highlight what samples have features at what characteristic size. And long story short, that is what we've done, and we've made a classifier out of that. And we were able to reveal that what particles are corresponding to what original pore size with very high accuracy. So on this slide, you see the result of that experiment, where in the center you see a characterization based on very high resolution CT. And on the left, you see the characterization based on this dark field analysis. And on the right, you see the difference. So it was a 90% accuracy. So I thank you for your attention. And to wrap up, yeah, this is also a story about using the image modalities that are at your disposal, and to be aware that you may need multiple ones to deal with the challenges of multi-scale analysis.